Hello, I'm MagNetCat.
And I'm a deterministic network verification tool, and I feel inadequate.
Okay.
I can't reason about failures or randomized routing, and my results are merely qualitative.
I don't know why you're so hard on yourself. I don't get it.
MagNetCat, why don't you say something positive about deterministic verification tool?
Okay, easy. Tool, you're a wizard with reachability properties, and you dress like a gentleman.
Well, MagNetCat, I guess you are a little better at probabilities and quantitative stuff.
Oh, thank you. It's really nice.
Even though it's completely juvenile and a waste of time.
Maybe you should come in once a week.
Hi everyone, let's see a probabilistic program P, where R and R prime are two sampling variables with the predefined probabilistic distributions as follows. The tick command incurs a cost of the product of x and y at each execution. Next, let's execute the program P and wait for its termination. Just kidding, we can find the program P terminates within the expected appropriate time, so we are curious about what the expected accumulated cost it triggered. Will it incur huge costs, generate huge debts, and finally deprive us of the freedom? Don't worry, we have a powerful weapon, polynomial cost martingales, which can help derive the upper and lower bounds for the expected accumulated cost of the probabilistic program. In this figure, we can see the curves of upper and lower bounds are very tight. And this is the two symbolic bounds. Here's our main contribution. First, in contrast to previous approaches that can only handle positive costs, our approach can handle both positive and negative costs. Second, previous approaches require the one-step cost to be bounded constants. Our approach can handle unbounded variable-dependent costs, which allows us to consider real-world examples. Third, while previous routes could only present sound upper bounds, our approach can provide both upper and lower bounds on the expected accumulated costs. This is the first approach that is able to provide lower bounds for expected accumulated cost. Welcome to our talk. Let's explore more details together.
GEN is a general-purpose probabilistic programming system that is suitable for a broad variety of probabilistic reasoning tasks. Here, GEN is combining symbolic and statistical reasoning to discover the structure in a time series. The possible structures are generated from a context-free grammar. Here, GEN is inferring the orientation of a camera relative to the floor from a video in real time. A user of GEN writes two programs. The first is a stochastic simulator that generates virtual worlds and virtual data collected from those worlds. The second is an inference program, which inverts the simulator to give virtual worlds that explain real-world data. GEN uses an extensible set of interoperable modeling languages that strike different performance efficiency trade-offs or support specialized classes of computations like deep learning. These features allow GEN to offer state-of-the-art performance on a number of challenging tasks.
We present ISOMB, an incremental symbolic inference framework for probabilistic programs. In situations with some loop-manipulated array data, upon which their probabilistic models are conditioned, undergoes small changes. To tackle the path explosion challenge, ISOMB is intra-procedurally path-sensitive, except that it conducts a meet-over-all-passes analysis within an iteration of a loop, conditioned on some observed array data. By recomputing only the probability distributions for the passes affected, ISYMB avoids expensive symbolic inference from scratch, while also being precision-preserving.